Okay, so hi everyone, and we're kind of at the home stretch now. So, you have your AP exam tomorrow, so good luck to all of you who are watching this video. We're just going to do a ton of practice problems from both Mech and E&M multiple choice to help prepare you for the exam and kind of refresh all those concepts for all the major topics that are taught in mechanics and electricity and magnetism. So we're going to start with mechanics and then we'll kind of transition into E&M. So the very first question is the uniform rectangular block in the diagram above is twice as tall as it is wide. It's prevented from sliding by a small ridge. So they're asking us for what angle of the incline will the block topple over. So basically the block is going to topple over when its center of mass is directly above the corner edge that is on the incline. The reason why this happens is that once you pass this point, the normal force, the torque provided by the normal force on the block is no longer going to balance the torque that is provided by the gravitational force on the block. So we're trying to find that kind of point of unstable equilibrium in this question. So from there, it basically becomes a trigonometry problem because we have we're basically trying to find the value of this angle or this angle because that is the same as over here. So if this total distance is L by 2, then half of it is L by 4. And then half of this distance would be L by 2. So then we know that from there, the tangent of theta would be equal to L by 4 over L by 2, which is just 1/2. So then theta is the arctangent of 1/2, which in degrees would be 26.6 degrees. So just a reminder to have your calculator on you during the test because you will need it for these numerical style questions. Choice A. So 24 is a conceptual question. So we have these two configurations and they want us to rank or compare the ratio of the angular frequencies of the two configurations. So the answer is B. And what I want you to remember about these simple harmonic motion problems is that you're always going to have something in the form of kx plus c is equal to m d squared x over dt squared. So in this case, the c value would be some constant force, which in this case would be the mg sine theta component of gravity. Kx will be the position-dependent force. It could be the spring force or it could be something else. And m is obviously the mass, constant value, and d squared x dt squared is the acceleration. So you're always going to have this kind of differential equation, and always for these questions, the omega squared value is equal to k by m, or the constant in front of the acceleration value dividing the constant in front of the position value. And that is the angular frequency solution to this differential equation, always. And it's always for simple harmonic motion, all the differential equations are always going to have the same form. So that goes for springs, but it also goes for LC oscillations and LCR oscillations and the like. So if you know the differential equation, even if you forget the formulas, you can actually derive them on the spot. So the C, the constant force value or the constant in these differential equations doesn't actually change anything for the omega values, so the ratio is still the same. What would change it is if we changed the mass between the two configurations or if we changed the springs that we use to achieve a different equivalent spring constant. But in this scenario, we're not doing either of those two things, so the ratio still stays the same. So over here, we have a work and energy problem. So delivery boy wishes to launch a package of mass m up an incline with sufficient kinetic energy to reach the top of the incline. The plane has length d and inclination phi and kinetic coefficient mu of friction. What is the minimum initial kinetic energy? So basically, in these types of problems, we're assuming that the block starts at rest and it ends at rest. So what that means is that the net work is 0 because the change in kinetic energy is 0. So what that means is that the work supplied by the person has to be equal to the work supplied by friction plus the work supplied by gravity. Since work supplied by friction and gravity would be negative in this case, we're trying to achieve a net work of 0. So in that case, the work of the person would be the work of friction plus the work of gravity. So hopefully by now, at this point in the year, you should know that for an ideal situation with just a single mass on an incline, nothing else crazy happening, the normal force should be equal to mg cosine theta. So then by extension, the kinetic frictional force should be mu mg cosine theta. And then the parallel component of the distance in this case would just be d, because d and the force of friction kinetic are just in the exact same direction. So that would be the work due to friction would be mu mgd cosine theta. Then the work done due to gravity would basically, there's kind of two ways of doing this. You could either find the component of gravity in the parallel direction and then multiply by d, or a shortcut is the work done by gravity is just the change in gravitational potential energy. If we assume the gravitational potential energy over here is 0, then the gravitational potential energy over here has to be mgh, and h in this case would be d times the sine of theta. So mgd sine theta. So if we add those together, we get option D. So we're just factoring out mgd from both of them. We get mgd times sine phi plus mu cosine phi. So here we have a rotational dynamics problem, a rolling problem. So we have a solid sphere of mass m, and it's released from a height h on an inclined plane. Basically, they want us to find the translational acceleration down the incline. So we are going to set up our force equations and our torque equations. So we have mg sine theta minus f is equal to max. And then for torque, we have f times r is equal to 2/5, sorry. It's a solid sphere. 2/5 mr squared times alpha. Normally, they'll give you those rotational inertia values. So what we want to do in this case is solve for alpha first, or the angular acceleration. So we'd get alpha is equal to 5/2 f by mr. So then we can make, using our rotational rolling equations, we know ax is equal to alpha r. So then that would be equal to 5/2 f by m, which we can then substitute back into here. So then we know that mg sine theta minus f is equal to m times f by 2, or 5/2 f by m. And then we get that 7/2 f is equal to mg sine theta. So then f is equal to 2/7 mg sine theta. And then what we can do is we can take this and then plug that back into here. And when we do that, we should get 5g sine theta, or phi. I'm kind of switching now between theta and phi, over 7, which is choice E. Just something to keep in mind. On exam day, if you ever, especially for the multiple choice, if you ever forget how to actually calculate the translational acceleration using the moments of inertia and torque equations and the net force equations, you can just remember this handy formula. Ax is equal to g sine theta over 1 plus beta for an object that's rolling down with rotational inertia beta mr squared. So for the solid sphere, the beta value was 2/5. So when you add 2/5 to 1, you get 7/5. And you're dividing by that, so you flip the fraction, you get 5/7. So, which is the exact same value that we got here, 5g sine phi by 7. So if you ever forget how to actually derive these equations, you can just plug this handy formula in, at least for the multiple choice. Ideally, you should know how to do this, but in order to maximize the number of points you get, this is something you can keep in mind. So number 40 is a gravitation question. So which of the following is an accurate mass versus radius plot for a galaxy obeying Newton's laws of gravitation and Kepler's laws with a constant orbit speed? So basically, whenever we have these types of questions relating orbit speed to mass, we first always look at the centripetal force because we're having something orbit in a circular path. So we know that the sum of the forces centripetal should be equal to mv squared by r. So in this case, we have gmm by r squared, which is the gravitational force, is equal to mv squared by r. V is constant in this case, and m, the mass of the individual object, is irrelevant. So basically what we're looking at is the mass of the, if you were in the galaxy, right? If you were over here, you're basically looking at the mass that is inside relative to you, which is causing a gravitational attraction force on you to the center of the galaxy, which is providing the centripetal force for you to move in a circular path, which is this mass value here. So if we just simplify, we should see that the m is proportional to r squared divided by r if we multiply both sides by r squared. So that means that m should be proportional to r, which suggests that there should be a roughly linear relationship in an ideal circumstance, which is what we're dealing with in this question. So we would choose choice C. So this is a very common type of question where you're just going to kind of manipulate variables to evaluate the proportionality between two variables and then use that relationship that you find algebraically to determine what the graphical scenario would look like. So 41 is a moments of inertia question. So we have a rod with variable mass density. So it's not your standard rod, so we're going to have to use calculus to actually determine the moment of inertia. So we know that the calculus formula for a moment of inertia is the integral of r squared dm. So whenever you have any kind of variable mass density problem, you want to start with the dm. So dm by dl in this case would be equal to the linear mass density, which in this case, or the mass per unit length, which in this case they told us is equal to L. So that's the variable part. So that would be equal to L. So then dm is equal to L dl. So when we substitute the stuff in, we go from 0 to L, because we're starting here and going here, of L squared times dm, so L dl, which is the integral from 0 to L of L cubed dl. So that should be, hopefully you remember your calculus, L to the 4th over 4, which is choice C. Number 42 is a conservation of angular momentum problem. So a circular platform of mass m and radius r rotates about a fixed pivot, and a boy starts on the platform and then jumps off after with tangential velocity v. We want to calculate what the final angular velocity of the platform is. So whenever they say circular platform, unless they specify otherwise, we always assume it is a uniform disk, basically, with rotational inertia 1/2 mr squared. So we know that the initial angular momentum has to be equal to the final angular momentum. So initially, we have the angular momentum of the disk that's spinning, which is 1/2 big M r squared omega. We have the angular momentum of the boy, which is little mr squared omega. We have, and then afterwards, we have the angular momentum of the disk, which is once again 1/2 big mr squared omega f. And we have the angular momentum of the boy, which afterwards, we basically just treat him like a point particle moving tangentially with angular momentum mvr. Okay, so from there, we just need to solve for omega f. So we get that mr squared omega plus 2mr squared omega minus 2mvr R is equal to mr squared omega f. And then if we do our algebraic division, we get omega f is equal to 2m plus m omega r plus 2mv divided by big MR, which is choice C. So whenever we have any kind of whenever we have any rotating bodies either colliding or mass being added or removed, you need to remember that we're going to use conservation of angular momentum. Most importantly, if you have an angular collision, especially if there's some kind of a linear impulse being provided, you cannot use conservation of linear momentum. For example, if I have a rigid rod attached to a mass and I collide that with another mass attached to a rigid rod, for that attached to pivots, you cannot use conservation of linear momentum in that scenario because the rigid rods will provide a linear impulse on the blocks. So in that case, you have to use conservation of angular momentum. The only exception to that is a ballistics pendulum, which is when you have a mass attached to a string. Because the string we assume in all these situations to be massless, and because it's massless, it can't provide an impulse on the mass. So if you have a string, then you can use conservation of linear momentum. That's a ballistics pendulum. But if it's a rigid object, you cannot. You need to use conservation of angular momentum. Okay, so on to E and M now. So the very first question hopefully should be pretty easy, but we have 3 resistors in parallel, and we want to determine the equivalent resistance. So remember that for resistors in parallel, the equivalent resistance is 1 over R1 plus 1 over R2 plus ... But in this case, it would just be R divided by 3 because they all have the same resistance of R. So basically, if all your resistors have the same resistance, then if you put N of them in parallel, then the equivalent resistance overall is just R divided by N. Again, this only works if they all have the exact same resistance, but it's these kind of time-saving tricks which can really be the difference between finishing the multiple choice section and not finishing the multiple choice section. And for the most part, in these types of situations, when they give you lots of resistors in parallel or in series, they usually have the same resistance. So if they do, you can just quickly know, okay, if I have 4 of them in parallel, it's going to be R by 4. Or if I have 12 of them in parallel, it's going to be R by 12. So using those kind of quick time-saving measures, especially for the multiple choice. So answer A. 54. So which of the following 4 configurations have the largest net magnetic field at the center of the Amperian loop? So for this, we just need to apply Ampere's law. Very common type of question you'll see on the multiple choice because there's no calculation involved. So we know that Ampere's law is the magnetic field basically is proportional to the enclosed current for a uniform Amperian loop. So basically we just need to determine which one has the greatest enclosed current. And remember, enclosed current takes account whether the current is positive or negative. And we consider it to be, you can define your system however you want, but usually we consider positive current as that which is coming out from the page, and negative current that which is going into the page. If you have multiple loops, for example, something like this, it can get a little bit more complicated. So for that, what you need to do is actually use your right hand rule. So stick your thumb in the direction of the current and then see which way your hand is curling to determine whether the 2 currents in 2 different connected loops are actually both positive or both negative. But for a simple Amperian loop like the ones in this scenario given, it's just find which one has the greatest net current. So what we need to do is, so A, the net current is 0, so it can't be that one. B, the net current is positive, so we want to Keep that one in mind, but keep looking at the rest of our choices. C, the net current is also 0. D, the net current is more positive than B because there's no current going into the page inside the Amperian loop, so the answer is D. I'll just give you a quick example of a more complex scenario. So over here, let's say I have a current going into the page and a current going out of the page. At first glance, you might think that they're canceling each other out, but in reality, that is actually not the case. So if you stick your thumb in the direction of the first current, which would be into the page, your fingers are going to curl in a clockwise direction. So they would kind of be going like that. And if you it should be the other way. That current is coming out from the page. My apologies. So if you stick your thumb out of the page for that current on the left-hand side, your fingers should be really going in the counterclockwise direction. And if you do that for the current on the right, and you put it into the page from the perspective of that current, it should be going in the clockwise direction. But what you'll see is that clockwise for the current on the right is actually in the same direction as the current in the left. So you're kind of going, you're going counterclockwise, 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 but then over here you suddenly become clockwise again, you see? So they're actually in the same direction. So the net current, if each of them has current I, would actually, enclosed current would be 2I, not 0. So number 55, so the magnitude of the magnetic field between the plates of a parallel plate capacitor can be calculated if we have, so this really should say the electric field, not the magnetic field. But for this, we need to know Gauss's law. So if we look at one plate of charge, because a capacitor is basically just two plates of charge, we can apply Gauss's law. So we have the electric field, and then it is going to have cross-sectional area of A, but you have to count it twice because a plane or plate has two sides. So you have 2A, so E times 2A, so the integral of dA is just A, which in this case you have to count 2A for the two sides, and that's the charge on it over epsilon naught, which then we can simplify that to Q divided by 2A times 1 over epsilon naught. Q over A, of course, being the surface charge density, which is sigma, so sigma over 2 epsilon naught. And then for the actual net electric field for a capacitor is sigma divided by epsilon naught because of superposition, because you have two plates, obviously, in a capacitor, so the net electric field is just twice the electric field due to a single plate. But that basically means that the electric field inside a capacitor is uniform and it's not distance dependent. It only depends on the area charge density or the surface area charge density, which is option A, and just something to keep in mind. If you're drawing electric field lines from a capacitor, make sure you draw them straight so that the intensity of the electric field is the same no matter how far away from the capacitor or from one plate you actually go. 57 is an induced electromagnetism question. So a conducting loop in the plane of the page is partially inside a uniform magnetic field. What is the direction of the net force of the loop if the magnetic field strength decreases? So if the magnetic field strength decreases, then the induced magnetic field will be in the same direction as the external magnetic field. So that means the induced field is also going to be into the page. And if the induced field is into the page, then that means that the induced current, if we stick our thumb into the page toward our laptop screen, our fingers are going to curl in the clockwise direction. So the induced current is clockwise. And then from there, we know that the magnetic force on a current-carrying wire is I dl cross B. So whenever you're doing this, make sure you're considering the external magnetic field. That's the magnetic field that's going to be contributing force on a wire. not the induced magnetic field. For the current, though, of course, we have to consider the induced current. So we have to consider each one of these sides. So 1, 2, and 3. 4 doesn't count because we don't need to count 4 because there's no external magnetic field in that region. So we just need to apply our right-hand rules. So in region 1, we put our thumb in the direction of the current, and then we put our 4 fingers in the direction of the magnetic field, so toward our laptop screen. And what that means is that our palm will face in the direction of the magnetic force. So on this part of the wire, the magnetic force is going to the left. On this part of the wire, the magnetic force is going to the right, and on the bottom, it's going down. So that means that the net force is downward. So the correct option is D. So just make sure you're comfortable using your right-hand rules. There will be a lot of questions on E&M where they'll just ask you what is the direction of the magnetic force, what is the direction of the magnetic field, and all the different kinds of laws relating to magnetism, whether that be the simple QV cross B, the law of Biot-Savart, or the force on a current carrying wire due to an external magnetic field. They all have cross products in them, so you need to know how to use your right-hand rules. So 59 is another pretty basic question. So just finding equivalent capacitance, but these types of questions are super common on the AP test. So capacitors are different from resistors. It's the opposite. So if they're in parallel, you add them together, and if they're in series, you take the reciprocals and sum them that way. So for these two in series, their equivalent capacitance would be 2C times 3C over 2C plus 3C, which would be equal to 6 by 5C. And then for these two over here, it would be 12C. These two are in parallel with these two. So then we would have 12C times 6 by 5C over 12C plus 6 by 5C. And then if you do some algebra, you get 72 by 5 over 66 by 5C, which is 12C by 11, which is C. So the kind of shortcut formula I'm applying here isn't really a shortcut. It's just I've done the algebra so many times that I know that if you have 1 over R1 plus 1 over, or in this case, I can say C instead of R because that'll get kind of confusing. So if I have 1 over C equivalent is equal to 1 over C1 plus 1 over C2, if I want to calculate the equivalent resistance, I'm going to end up getting 1 over C equivalent is equal to C2 plus C1 over C1 times C2, and then if I flip it, I'm going to get C equivalent is equal to C1, C2 over C2 plus C1. So that kind of shortcut I'm just applying over here because I know it's going to be the first times the second over the sum of them. And that's another kind of time-saving thing that you can do during the exam. The amount of algebra that you can minimize, the faster you're going to get through the multiple choice. So another kind of thing to be aware of when you're doing these equivalence problems for both springs, resistors, capacitors, and inductors, you're going to be doing the same thing. So you might as well be familiar with the algebra rather than having to redo it every single time. 60 is ranking the magnitudes of currents. So basically looking at this diagram, we should immediately know that I3 is going to have the biggest current just from junction rule because we have I1 and I2 both coming in and adding together to become I3. So I3, of course, has to be the biggest. So that eliminates B and C right off the bat. And then to determine between I1 and I2, we can just look at the EMF values. E1 is greater than E2. So therefore, I1 has to be greater than I2 because the potential difference being provided is greater, resulting in a greater current just by Ohm's law. So for ranking, although we can't determine the exact value that way, we can get a ranking very easily just by looking at what the EMF value is, knowing that if the EMF value is larger, then the current will be larger as well. So the correct answer here is D. The only kind of caveat to that would be if the equivalent resistance values were significantly different. But in this case, they're quite similar, so that's not really an issue. But if they were drastically different, then we would actually have to break up the circuit, find equivalent resistances, equivalent potentials, and actually calculate the values. But over here, since they are roughly the same and the voltages are different, we know that the difference in voltage is more significant than the difference in the resistances, because the internal resistances generally are very small. So to get a ranking, we don't need to actually solve for the numerical values. 63. So basically we have a bar on an inclined plane, and we are trying to find the terminal speed of the bar as it moves down the magnetic field. So if we take the forces in the x direction parallel to the incline, we get mg sine theta, or phi. I'm going to say theta because we're going to have to deal with flux, so that might get a little confusing. Mg sine theta minus the magnetic force, and that has to equal 0 because at terminal velocity the net force is 0. So what we need to do first is calculate the magnetic flux. So the magnetic flux is B dot A algebraically, because the magnetic field is constant in here. We don't need to use an integral or anything. So we get B times, so the area is this length is little b, and then I'm going to call this length over here, x. So then the area is just bx. And then obviously cosine of theta, because the area vector here would be normal like this. The magnetic field is going straight up like this. So this is theta, this is theta. So then from there, in order to find the induced EMF, we need to do d phi dt. So that would be b cosine theta, and then dx dt, which would just be b v cosine theta. Then to find the induced current, we just need to do epsilon induced, or the induced EMF, over R, so just applying Ohm's law. So then we get b v cosine theta divided by R. So then we need to plug that back into here. So we get mg sine theta is equal to the magnetic force on, again, a current carrying wire. So we get I, which is BBV cosine theta divided by R. I, and then L cross B. So the length of the bar, or the wire in this case, is B. The magnetic field is B, and then we need to take the perpendicular component. So if we can, so the length vector, or this B vector over here, is in the direction of the current, which means that we have to consider the component of the magnetic field that's normal to that. So what basically, in essence, what we need to do is the magnetic field is going upwards like this. We need to consider the component that's normal to the length vector, or to the current vector. You can almost think of it, even though current technically isn't a vector. I'm just going to call it that, just for clarity's sake. So the angle between these two is also theta. So the normal component of the magnetic field is just b cosine theta also. So that means that over here we also have to multiply by cosine of theta. So then solving for v, we will get mgr sine of theta divided by b squared cosine squared theta, which is the same as choice A. So for all these types of problems, first thing you always want to do is find the magnetic flux equation, because from there you're kind of already setting yourself up for success, because once you have the magnetic flux, then you can find the induced EMF, find the current, find the force, and do all these things. So if you're ever stuck in an electromagnetism question, which you should be able to immediately tell it's an electromagnetism question if there's anything relating to terminal speed or changing magnetic field or changing area, or things are moving relative to each other, just find the magnetic flux if you're completely lost, and then you'll start coming up with ideas of, okay, I found the magnetic flux, do I need the current, do I need the induced EMF? Then you can plug that in to the equations and kind of patchwork together a solution, even if you don't necessarily know exactly how to solve it, as soon as you see the question. So 72 is an oscillations question. So I already went over this before, so I'm just going to kind of restate the same thing. So for the potential difference across an inductor, we have L di dt, and for the potential difference across a capacitor, we have Q by C, which can be rewritten as L d squared Q over dt squared is equal to Q by C. So rewriting it in the same form that I talked about earlier, we get d squared Q over dt squared is equal to 1 divided by LC into Q. So this is omega squared. So omega squared is equal to 1 by LC. So omega is equal to the square root of 1 over LC. So for all these kinds of simple harmonic motion problems, it's the same thing. Write the differential equation, and all the answers can be found from there. And if you have a kind of pendulum situation, you are going to get something in the form of mgl sine of theta is equal to I times by alpha, where alpha is just d squared theta over dt squared. For those types of questions, in order to derive it, you just have to assume that sine theta is approximately theta for small values. That's the small angle approximation, and then you can solve it the exact same way as any other simple harmonic motion question. And that's also why if in an FRQ or something they ask you if the angle value for a pendulum, any kind of pendulum, it could be a simple pendulum or a physical pendulum, if the theta value is very large, will it follow simple harmonic motion behavior? The answer is no, because for very large theta values, this approximation is no longer valid. So just something to keep in mind. And the last question is another electromagnetism question. So a small bar magnet falls through a solenoid at terminal velocity. So we want to look at what the relationship is between the induced EMF and time. So basically we're looking at d phi dt versus time. So basically just thinking about it conceptually, before it enters the magnet, the magnetic flux is 0. And the change in magnetic flux as a result also is 0, right at the instant when it starts falling. And same thing once it is completely out of the magnet, or out of the coil, sorry. So it has to start and end at 0. So just from there, we know D is not an option. And also, we know that at some point in the middle, it's falling with terminal velocity. So the velocity is constant. We know that the magnetic flux, once it's fully inside the coil, is going to be constant for at least an instant. If the coil is very small, that instant will be an instant, and if it's very large, that could be a while. But it has to reach 0 in the middle at some point. And as it's entering, the flux is getting bigger, right? So that means that if we consider the flux is getting bigger, the induced magnetic field we could say is in the negative direction. So the induced EMF is negative. And as it's coming out, the flux is getting smaller. We can say the induced magnetic field is positive, and the induced EMF as a result is also positive. And the only graph that follows that kind of oscillatory behavior is C. So everything else does not make sense for the scenario. So good luck tomorrow. Mainly, I just want you guys to keep in mind that if you don't know how to solve a question immediately, look at what the information is that has been given to you and try to look at all the equations that are at your disposal and think about how the given information would kind of fit like a puzzle into the equations. That's one way of solving a problem if you have absolutely no idea. Another way of solving a question if you have no idea, especially for mechanics, is to identify what stays constant. For example, if you know that momentum is staying constant, then you can apply conservation of momentum. If it's only conservative forces acting, apply conservation of energy. If you notice that there's a collision, but there are rigid bodies acting on each other with pivots and such, you know what's going to stay constant. It's angular momentum. So if you can identify what stays constant, you have a much better chance of actually being able to solve the problem just by setting up the equation of this starts the same and ends the same, and just by substituting stuff in, you can solve for the unknown which you're looking for. So I wish you all best of luck tomorrow, and I'm sure you are all going to do great. Make sure to pace yourself, make sure to charge your calculator, make sure to sharpen your pencils, bring your A game, do your best. You're definitely prepared, you've worked really hard, and I wish all of you best of luck for tomorrow's AP Physics exams.